Good morning. Let's see. First off, are there any questions on the Gauss's Law worksheet? Homework / lab thing?
Did you want us to fill it out on the worksheet, or did you want us to submit a separate paper like for our homeworks?
Oh, if you've got room, fill it out on the worksheet and then practice. You could type your answers into there, I guess, but probably some of them you're going to want to draw on maybe. And you can see if you can convert that into an uploadable multi-page PDF. So have you experimented with that? I think you've typed everything, haven't you, Nolan? Or
Yeah, I tend to type most things.
okay.
Handwriting's so bad.
Actually, I thought you had pretty neat handwriting. But anyway, yeah, if there's room, go ahead and do it on the sheet. And then if you run out of room anytime, actually, if you've got it, did I put it up there as a Word document? You could just introduce extra space into the Word document and, you know, put a bunch of spaces, do it on there. That way, when I'm grading it, I'll just flip through the pages easy enough and see what the questions are every time. That would be nice, I guess. Any parts where you're perplexed as to what I'm asking or what the situations are? Anything like that? I think it's part 4, those point charges and the spheres. May be a little bit difficult to picture at first, but I hope if you read those carefully. Number 2 on there, I think that one requires some integration if I remember right. Maybe number 3.
On number 2, we'd have to integrate to find the total charge, wouldn't we?
Right. Yes.
Okay.
Yeah. So that's a weird charge distribution where it varies with the square of the distance away from the center. So I think, I was at a physics teacher's meeting one time and they were talking about conceptually rich problems. And one that they dreamt up was something similar to this, except it was the Starship Enterprise is in orbit around some planet, and it's impossible for humans to survive on the planet, but there are caves underneath the planet. But the planet has this weird spherical charge distribution, and you have to figure out if it's safe to beam someone down to this cave that was like 150 meters beneath the surface or something like that. So it was a problem very much like this one, but hidden in a bunch of text speak, I guess, to try to understand what was going on. But yeah, you do have to do some work on those things. Similarly with problem 3, you've got an odd electric field that increases with the square of the distance along the z direction. So, oh, and did I draw this? Okay, I did draw the cubical Gaussian surface on there. So that was it on there. Well, no other questions on that thing. We're diving into a new topic today, and that is electric potential. And for that, I'm going to go back to gravity for a little bit here. Move junk off my chair. Back when we learned about gravitational potential energy,
You need to share the visualizer.
Oops. Yep. I clicked on the visualizer, but forgot to click share for it. Boy, I think I may have to go back to my old corded mouse. I think my cordless one is dying on me. Okay, but when we were learning about gravity, when we talked about the idea of gravitation on the surface of the Earth, where if we looked at the force that was acting on an object of mass m here, the force would be downward and in the direction of the gravitational force. And when that was the case, gravitational potential energy increases. So GPE increases as you go up, and it decreases when you go down. And so it actually increases if you move an object in the direction opposite the force, and decreases if you move an object in the direction of the force. And a rough definition of changes in potential energy between 2 points, and actually it's not so rough, it's carefully defined. If you've got a delta U, which is going to be the difference in potential energy between a 0.2 and a 0.1 due to some force, it will be the negative of the work done by the force, F dot ds, as you go from 0.1 to 0.2. And so that's kind of a weird definition of the change in potential energy for any old force. Well, now we've got this electric force, and let's imagine that we've got some big charge here, Q, and maybe this big charge is a spherically symmetric charge distribution on a plastic ball that's got a mass of a few kilograms. Okay, so that'd be a large plastic ball, but if it's solid, it could have that. And then we have some other sample charge, or a test charge is the way they're often referred to, that we'll call Q naught. And Q naught might just be something like a proton. And we're going to imagine that we start off with this Q naught, a distance R1 away from the center of this charge distribution. And the charge distribution outside of this plastic sphere is going to act as if all of the charge is concentrated at the center. And so that'll be our center of force, if we want to think of it that way. And then we're going to move it out to a distance R2 out here somewhere, a larger distance. Okay, what's the change in electric potential energy for this thing when it does that? Well, I can use this expression to figure it out. I'll have U2 minus U1 is going to be the negative. What's the force going to be? Well, I could just write it as Coulomb's law, but I'm going to write it as the Q naught times the E for the electric force for this thing, which is just going to be KQ over R squared along R hat. That is the force, this is the electric field right here. If I multiply it by Q naught, it becomes the force that's acting on that charge Q naught. And so I have that, and then I'm going to dot that with my little increase in my vector change in position as I go out here. And that could be just written as simply as dr in the r hat direction. So it's just going to look like that. And I'm going to integrate from R1 to R2. And this turns out to not be bad integral to do because a lot of the things that look scary in here end up going away for us. Like we can pull the K and the Q naught outside of here, and I'll get U2 minus U1 is equal to minus Q naught KQ. And then inside, I've got an R hat dotted with an R hat. A unit vector dotted with itself is just 1, so that's gone. And the only thing left inside the integral is dr over r squared. And so integrate from r1 to r2 of dr over r squared. That integral is just minus 1 over r. I've got a minus sign here, and well, maybe I'll try to keep it straight here. Minus Q naught KQ over times minus 1 over R, evaluated at R1 and R2. Like that. Well, a minus and a minus give me a plus here, and I'll have U2 minus U1 is going to equal Q naught times K times Q times 1 over R2 minus 1 over R1. And so that would be the difference in potential. Now, suppose I decided that I was going to let R2 be infinity. And I'm going to make the choice that the potential energy will be 0 when it gets out there to infinity. This is very much like the choice we made with gravitational potential energy when we, instead of looking at this situation, we looked at the idea where you might move a large distance compared to the Earth's radius. And we ended up with a different sort of expression. So let R2 equal infinity and U of infinity equals 0. That'll be our choice for where gravitational or this electric potential energy is going to be 0. And in fact, that's the conventional choice for places where we have charge distributions, especially point charges. Sometimes we'll let the potential energy be 0 at different points, like electrical ground or something like that. But for this, we'll do that. Well, if that's the case, if U2 is going to be infinity, or R2 is going to be infinity, and U2 is going to be 0, this thing just becomes minus U1 is going to equal minus, I'll have another minus sign, minus K Q naught Q over R1. And this is what we'll use, actually, since there's a minus sign on both sides of that thing, I can get rid of that. For 2-point charges, the potential energy is just going to be K Q naught Q over R. And so that's a fairly simple expression. It's different from the electric field. It's not a vector for one thing. This is a scalar, and it's only got an R down there on the bottom. Okay, well, let's see. We can use that to do something like, oh, by the way, this is electric potential energy. And we've got a situation here, we're going to have to be careful with how we word things, because we're shortly going to be looking at more complicated situations. And we could start off with this sample problem. I haven't posted these sample problems up there yet, but this one's fairly simple. 2 charges are separated by 5.00 nanometers. One of the charges is plus 2e and the other is plus 1e. And in parentheses, I put, what do you suppose these things are? What could possibly have a charge of +2, and what else could possibly have a charge of +1? E. And remember, E by itself means 1.60 times 10 to the minus 19th coulombs. Wild guess for that one?
Just be a proton. And
Yeah.
The other one could be an alkaline earth ion of some type.
Okay, I was just thinking of an alpha particle, which is a helium nucleus, helium-4 nucleus.
That works too.
But yeah, but an alkaline, an ion with a charge of +2. Although, let's see, I guess you could have that ion and a proton be separated by 5 nanometers. 5 nanometers is actually fairly large. It's bigger than just the size of an atom. So, but anyway, what's the electric potential energy of this group of charges? Well, let's see. We can just use our formula here. And instead of K Q naught Q, I'll call it Q1Q, okay, over R. So K is going to be our 8.99 times 10 to the 9th Newton meter squared per coulomb squared. And then our charges here, 2E times 1E is going to be 2 times E squared for that part. And the R is the 5.00 nanometers. So 5.00 times 10 to the minus 9th meters. Oh, and E being 1.60 times 10 to the minus 19th. There it is. And that I have to square, divided by 5EE minus 9. Okay, and it's not much energy. It's about 9 point, I guess we can keep 3 sig figs here, 21 times 10 to the minus 20th joules is what I get for that thing. So in joules, at least, it's not very much. We're shortly going to learn about a new unit of energy that is a more convenient unit for when you're dealing with stuff on this level. And it's called an electron volt. But we don't know what a volt is yet. So let's investigate something else here. Let's suppose I decide, instead of wanting the potential energy of this particular charge configuration over R, maybe I want to stick a bunch of different charges in there, and I don't want to have to go through the trouble of calculating the KQ over R part every time. Instead, what I'll do is calculate the charge, or the potential energy per unit charge of that particular charge at that some particular distance. And when I do that, I would just have KQ over R. And so for some particular charge, I would pick a particular distance from it and call that the potential energy per unit charge at that point, which is going to be a weird idea. Energy is abstract already, and now we're taking it to a further level of abstraction. Potential energy per unit charge. That's kind of weird. by the way, this thing that we calculated up here, the potential energy of these two charges, that's how much work we would have to do to bring a proton from infinity to where it's only 5 nanometers away from this either, well, the doubly charged ion, doubly charged positive ion, or a helium-4 nucleus. But we'd have to be fighting against the repulsive force between these two things all the way in, and that's the amount of work that we would have to do to get them to that distance apart. So that's what the electric potential energy of them happens to represent. If I'm talking about the electric potential energy per unit charge, it's going to have weird units of, let's see, joules per coulomb. So let's see, I'll write it in lowercase first. Joules per coulomb, or J over C. And that particular combination of units we call a volt with an uppercase V. And so, well, that's kind of a different thing, but this would be the electric potential of a charge Q at a distance R. Oh, I didn't tell you that term yet. Instead of calling this electric potential energy, this stuff, its potential energy per unit charge, we just call it electric potential, and we leave the word energy off of it. So kind of a tricky definition. So we have to be a little bit careful with our definitions of these things. Well, let's see. Let's figure out what the electric potential is just 5 nanometers away from this charge of plus 2e. That's a reasonable thing to calculate. So, oh, by the way, this is another place where things get confusing. The abbreviation for the unit of electric potential is capital V. That's often the symbol that we use to stand for electric potential. And so a lot of times somebody or a problem will ask you to calculate the electric potential a distance r away from something, and you'll use a V to stand for the thing that you're calculating as well as for the units that it's measured in. And so I don't know, just have to be careful with that stuff. But sometimes if you put a subscript on the V, you can talk about it being the V at some point. And then and it would be the voltage at that point, with voltage being considered 0 at infinity. I don't know. It's just something you'll have to wrestle with. So we'll keep our eyes on things. Anyway, we want the electric potential 5.00 nanometers from a charge of plus 2e. Okay. So it would just be, I'll call it V sub 5 for the electric potential energy 5 nanometers away from there. So it would just be K Q over R, and I just plug in the numbers. 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. And then Q would be 2 times 1.60 times 10 to the minus 19th coulombs. And I divide by the 5.00 nanometers. Unit-wise, this meter will cancel or divide with one of these and just make it Newton meters there. This coulomb will divide with one of those coulombs here and just make it Newton meters per coulomb. But a Newton meter is a joule, so that's joules per coulomb or volts. And a lot of times on these problems, I'll actually write out the word volt so that I don't confuse the V on one side with the V on the other, and that'll work sometimes. Okay, and I get about 0.575 volts would be the electric potential that far away from that particular charge, whether it's an alpha particle or something else. It's easier for me to imagine an alpha particle since I don't get to play with chemistry much anymore. But in fact, I haven't much since I took that class as an undergraduate. But that's the idea on that one anyway. Okay. Actually, before I do this problem, which is an electron and a proton separated by the Bohr radius, I'm going to introduce the idea of something called the, what I did with that sheet. Oh well, called the electron volt. And the unit looks like, whoops, it's a lowercase e with an uppercase v. And so that's the way you abbreviate that unit. And an electron volt is the kinetic energy, this is a definition of it, acquired by an electron, and it doesn't have to be an electron. Turns out it could be anything with the same charge as an electron, but electron's easiest to think of. When accelerated across a potential difference. Now, when we say potential here, we just mean electric potential. And a potential difference just means a difference in electric potential, but we just call it potential difference. Of 1 volt, and it'd be 1.000 volts. It's just defined to be this. So let's imagine that we have some region of space, and you have to think about how this is going to work. We'll imagine that the electric field points in this direction, and here is the initial position of the electron, P initial. Okay, if the electron or the electric field in space, we'll imagine that this is a place where you have a uniform electric field that points in the same direction with the same magnitude. So this could be the electric field between two metal plates that are close together, something like that, like the things that they used to have in TV sets for changing the direction of the electron beams. But anyway, here's its initial position, and here is its final position. And we'll imagine that, now remember, the electric field points in the direction of decreasing electric potential. So V initial might be the electric potential anywhere along this thing. V final is the electric potential anywhere along this imaginary plane here. And this electron that we've got here, E minus, will be accelerated in the direction opposite the electric field. And something that we'll have is that if it's accelerated from rest across that thing, let's see, I should say when accelerated from rest across a potential difference of that. Okay, so here's the difference in electric potential energy for this electron. Delta U is going to be Q delta V for the electron. Now, V final minus V initial is going to be 1 volt. Let's see. Yeah, that'll make sense. It'll have a negative change in potential energy, but that lost potential energy is going to show up as kinetic energy. So I can set this up this way. Let's see. I can call this U final minus U initial is going to equal Q delta V. Now, the charge on the electron is negative. V final minus V initial would be 1 volt plus 1 volt in this case. So U final minus U initial is going to be minus E. E is the abbreviation for the charge on the electron, times 1 volt. And so that's the 1 capital V there. A volt is a joule per coulomb, and so we'll have that being the case, but that will show up as kinetic energy of this electron. And so I could say that, write a conservation of energy thing. I can have, whoops, 1/2. I don't know where 1/3 would have come from. 1/2 mv initial squared, which is actually 0, plus U initial will equal 1/2 mv final squared plus U final. I'm running out of room. I'll get a different sheet somewhere. Okay, this is 0. Let's see, 1/2 mv final squared is going to equal U initial minus U final. And U final minus U initial was that thing. This will equal minus E times the 1 volt. So the reverse of that will equal plus E times 1 volt. Now, by definition, this will equal 1 electron volt, but this thing is going to equal the charge on the electron, the sign or the magnitude of the charge, 1.602 times 10 to the minus 19th coulombs, times 1 volt, which is a joule per coulomb. And so it turns out that 1 electron volt is equal to 1.602, and however, you could keep going forever on this, just plain joules times 10 to the minus 19th joules. And so anytime we've got an energy for some charge distribution and it ends up being some tiny amount, we can convert it into electron volts and we get a unit of energy that's more convenient for dealing with things at the atomic energy level. And in fact, electron volts and multiples of them are typically the units that you deal with. When I go to a dentist office, actually the one I'm going to now, they're pretty prompt and they don't leave you sitting in the chair for long periods of time. But it used to be I'd go to the dentist and first you'd start sitting off out in the waiting room for 20 minutes reading magazines that are 8 months old or something like that. And then they'd call you back into the exam room. And sometimes you'd sit in there for half an hour before anybody showed up. And I'd left the magazine. I finally found an article in that I liked out in the waiting room. So I'd go crazy. But I'd read everything in the dentist office. And something that I noticed in the dentist office was the x-ray machine. And on the side of it, it said, it had this written, 41 keV. What in the world is that? Well, it turns out that's the energy of the x-rays that the machine emits. They're measured in electron volts, but it's 41,000 electron volts. The K meant kilo. And so that's a unit that shows up. On the nuclear scale, when you're talking about energies there, instead of dealing with KeVs, you might deal with units of MeVs. And that's mega electron volts. Dealing with the mass. This is something we'll talk about at the end of the quarter when we study relativity. But the mass unit that we always used in nuclear physics when we were talking about neutrons or protons was a unit that looked like this, MeV over C squared. And the mass of a neutron or a proton happened to be about 940 MeV over C squared. Where in the world did that come from? Well, it comes from this. E is equal to mc squared, and if you take the energy of it and divide that by c squared, you get a mass. And so the rest energy of a proton or neutron, that's the energy it has just because it has mass, it's called rest energy, is about 940 MeV. And if you divide that by c squared, you have an effective mass for the thing. It's a bit of work to convert from this to kilograms, but it can be done. But you tend to just stay in these units all the time. So odd places that electron volts show up anyway. So let's take a look at this electron and a proton separated by the Bohr radius is what this is called. And in Bohr's original model of the atom, which he came out with in, I want to think 1913, but I'm not positive. It's right around there somewhere. He had the electron orbiting the nucleus of the atom. And we tend to look at this as if it's the last thing that Bohr ever did. But actually in the 1920s, he was very instrumental in guiding a whole group of physicists who were working at his research institute in Denmark. And he guided them toward the understanding of the atom that we still work with today, the quantum mechanical model of the atom. And so Bohr had the first step in that direction with his model, but that's not where he stopped. He kept going. And then he later did lots of stuff in nuclear physics as well. So they're separated by that much. And what's the electric potential of this system of charges? Well, it's just going to be U is the electric potential energy, and that would be KQ1 Q2 over R. So we'll do this and we'll get an answer in joules first, and then we'll calculate it, see what it is in electron volts. And so 8.99 times 10 to the 9th Newton meters squared per coulomb squared. And the charge of each of these things is the same. If we're just after the magnitude of the potential energy, or we can go for the sign too. One of them is going to have a charge E, and the other is going to have a charge minus E. And in each case, E is 1.60 times 10 to the minus 19th coulombs. And so this will be a negative potential energy. Okay, when you have charges of opposite sign, you'll have to be exerting a force opposite the attraction as you bring in a force so that it doesn't accelerate on the way in. Or you can think of the energy that we'll end up with here as the amount of energy that you would have to completely tear these things apart. And so there's something that'll happen. Okay, R down here is that number, 5.29 times 10 to the minus 11th meters. So let's see what we get. 8.99 times, whoops, that's got a multiplier on it, EE, 9 times 1.60. It could be 602, but I'll just go with 3 sig figs. EE minus 19th squared, because there's 2 of them, and then divide by the minus 11. And I get a value of minus 4.35 times 10 to the minus 18th. Let's see, coulombs times coulombs is coulombs squared. That'll divide out with those. Newton meter squared divided by meters are Newton meters. So this is just joules. But then I'm going to multiply by 1 electron volt over 1.60 times 10 to the minus 19th joules. So what do I get? Get about 27.2 electron volts. Okay, that's a reasonable energy for something at the atomic energy level, or the atomic level, electrons in an atom in particular. 27.2 electron volts. If you've taken the majors chemistry, oh, it's got a minus sign on it. Did you ever learn anything about an energy of minus 13.6 electron volts? Does that sound familiar? It's exactly half of that, happens to be. This is, if you ever see an energy level diagram for the hydrogen atom, it'll have an energy up here at 0, or it depends on which way you start the numbering from. And then it's got a bunch of various energy levels for atoms or electrons in the hydrogen atom. And the lowest energy level is minus 13.6 electron volts. Okay, half of that. Turns out this would be the energy of the electron in that atom, but part of its energy is kinetic energy. And so the combination of the kinetic energy and this negative potential energy, or electric potential, or electric potential energy in that case, give it a combined energy of minus 13.6 electron volts. And so this ends up being how much additional energy you'd have to give to the electron in the ground state of hydrogen to liberate it, to be able to free it from the atom, because that's its electric potential energy. But because it has some kinetic energy down there, and an amount equal to half of that, actually it's an amount, well, it's positive. Kinetic energy is always positive, but that ends up bringing its total energy up to this level here. So anyway, there's not much when you're looking at it in joules, but in electron volts, it's a reasonable amount. And it's a whole lot easier dealing with energies of electron volts as opposed to joules. You don't have to be carrying around this times 10 to the minus 18th or minus 19th all the time. So that's just easier. Okay, moving on with this thing, we have a uniform electric field of magnitude 250 volts per meter. Oh, we haven't talked about this. Odd unit, haven't seen that one before. The electric field, which has units of newtons per coulomb. Okay, those are our units for it. If you multiply top and bottom of this thing by meters, okay, you're not changing the units because meters over meters is just 1, but a newton meter is a joule, and so you would get joules per coulomb meter, and a joule per coulomb is a volt, and so the electric field units that we sometimes write as newtons per coulomb could also be written as volts per meter. And sometimes that's a more convenient unit, sometimes this is. It just depends on the particular application. But seeing it expressed this way is sometimes a good way to think of it. If you have a strong electric field, you'll have a high number of volts per meter. And that means as you go from one place to another place, there will be a large potential difference between those two places. If you have an electric field that gets very strong in air, for instance, it becomes strong enough to rip the electrons off of the atom, and then you don't have much of an electric field anymore. The air is no longer an insulating layer. It becomes a conductor when you have a strong enough electric field, and you get a spark or a lightning bolt if you have enough charge available to make such a thing. So this is a reasonable way of thinking of the electric field sometimes, and it's also kind of handy. So uniform electric field, 250 volts per meter, directed in the positive x direction. Okay, so here's E in the positive x direction, and the magnitude of E is 250 volts per meter. A 12 microcoulomb charge moves from the origin to the point X and Y equals 20 centimeters, 50 centimeters. What was the change in the potential energy for this charge? Well, if the electric field is everywhere in the region this thing is moving through in the X direction, so you could imagine it, well, it said it started at the origin, so here's its initial position, and its final position is 20 centimeters out here in the X direction, but 50 centimeters up in the Y direction. My scales are different on the two axes, but that's okay. So this would be 20 centimeters, 50 centimeters. And so it moves from here to here. Well, the change in potential energy is the same whether I move it this way first and then this way, or whether I take it along a line that goes like this. When I've got the electric field that's only pointing to the right in here, I can bring that charge out to here. What am I moving? Positive 12 microcoulomb charge. And when I move it up here, I'm moving sideways relative to the electric field. So it's like moving something horizontally in a gravitational field. Gravity does no work in that case. Remember, the work done by a force is F dot R. And if the R happens to be perpendicular to the force, the dot product will be 0. Remember, it's got magnitude of this, magnitude of that, cosine of the angle between them, and the cosine of 90 degrees or 270 degrees is 0. So, all right. So all that matters is that we move 20 centimeters in the X direction. Now, will the change in potential energy be positive or negative in this case?
Would it be negative?
Yeah, it would be negative because the force on the charge is in the direction of the electric field because it's a positive charge, and effectively it's going downhill in the electric field. It's like when you drop a rock, gravity exerts a downward force and the rock is moving downward. It's losing gravitational potential energy. And so same thing here. We'll have a negative change in the potential energy of this charge. And in this case, the force on the charge is going to equal Q times E. Okay. The work that's done in this case, when you have a uniform electric field, you don't have to worry about integration, at least when you're, when you've got a uniform field. The work that's done by the force in this case is going to be Q times E dot the displacement, which is, I'll just call it D for the displacement. And the work that's done by this force is the negative of the change in potential energy. That's the way that it works. And D in this case is going to be 0.20 meters. I'm assuming that we can keep 2 sig figs on this. Meters in the I hat direction. So the change in electric potential energy that it asks for, so delta U, is going to be the negative of the work, which is in this case going to be minus magnitude of the charge, magnitude of the electric field times the displacement. E is in the I hat direction also, so I would have for the work, I'd have Q E I hat dotted with 0.20 meters I hat, and I hat dot I hat is just 1. So it's just ends up being minus QED for a uniform electric field. That's something to be a bit careful with. You can't apply this if you've got a non-uniform electric field. It's not so simple. Then you have to integrate. But it'll just be delta U equals minus 12 times 10 to the minus 6th. It's a microcoulomb times the electric field, 250. Now, in this case, once we get to this point, forgot to start with the door shut today. It's a volt per meter, but I could also think of it as a Newton per coulomb, and it's probably easier at this point to think of it as a Newton per coulomb. Although, if I thought of it as a volt per meter, yeah, either way, we can do that. Oh, and then 0.20 meters. So just multiply that string of things together, and we will get minus oh, I could have done most of that in my head, maybe all of it if I'd been thinking. Anyway, minus 6 times 10 to the minus 4th. Now, unit-wise, the coulombs go away, and I'd get Newton meters, which are joules. So that would be the loss in energy of it. And this is big enough numbers that electron volts probably wouldn't be necessary on a problem like this. Now, through what potential difference did the charge move? Okay, let me show you how we can define electric potential difference. Let's see. When we have an electric field, it actually ends up looking like this. Delta V is just minus, whoops, forgot a V on here. This represents change in potential, and it's one of those, well, it will have units of volts, I guess, so there's that good, but it ends up being the negative of the integral of E dot ds. And in this case, it's not going to be horribly interesting, but we'd go from the initial position to the final position in order to be able to figure this thing out. And in this case, it would look like, it's not going to be very hard actually. My electric field is 250 volts per meter, 250 volts per meter in the I hat direction. My ds, I'm going to be dotting that with dx, which is also in the I hat direction. And then I'm going to be going from 0 to 0.20 meters. And if I take care of stuff inside this integral, I'll have I hat dot I hat, which is 1. 250 volts per meter is a constant that can come outside. So minus 250 volts per meter. And then left inside the integral, I end up with 0 to 0.20 meters of dx. Well, the integral of dx is just x, evaluated at 0.20 meters and 0 meters. This ends up being a really simple multiplication, minus 250 volts per meter times 0.20 meters. 0.20 is a fifth of a meter, and so I end up with minus 50 volts. So going in the direction of the electric field is going in the direction of decreasing potential, and the potential decreased by 50 volts. The absolute potential, we don't know in this situation, but we do know we can calculate the change in the electric potential due to that electric field as we go from one point to another. But for something like this, you'd probably have to pick some place and define it as the 0, because if you've got a uniform electric field like this, it's not due to a point charge where you can say it's 0 at infinity or anything like that. Not quite so simple. By the way, if you do have a uniform electric field and it's pointing in some direction like this, and maybe you're going from 2 points that are separated by a distance d, the change in potential in this case, going from here to here, is just minus E times D. So ed, something like that. And if you go opposite the thing, opposite the electric field, the increase in potential would be this thing with a plus sign. So E points in the direction of decreasing potential, but if you go opposite E, you're going in the direction of increasing potential. And if you have a uniform field and you're moving parallel to it, it's just equal to, the change in potential is just equal to that electric field times the distance that you move along a line parallel to the electric field. So in this case, we actually went parallel to the electric field for a while, 20 centimeters, and then perpendicular to it for 50 centimeters, but there's no change in the electric potential if you're going perpendicular to the field, because the electric field does no work when you move perpendicular to it. So more ideas. whoops, lost something on there. This is the old style TV set. If you ever opened up an old TV set, or the sticker was probably on the outside before you opened it up, but there would be a warning sticker on it there that said danger, high voltage. And this is the old old kind of TV set that or computer monitors for that matter. They had a picture tube is what they called it in it. It was also called a CRT for a cathode ray tube. Electrons are cathode rays. That's a really old name for them. But it would have a thing that stuck out a long ways behind it. And inside of this thing would be a vacuum, and there's a little electron gun back there. And it would have accelerating plates that were charged with a potential difference of about 25,000 volts. And they would keep them charged with a device called a capacitor. That's something in the next chapter. And it would stay charged for a while after you turned the TV set off. And so if you ever opened up one of those things, you had to be really careful not to give yourself a nasty shock. There was a phrase or a question that they would ask of people. If you're going to be working on something with high voltage and you have to reach in with your right hand in order to do something in that region, where should your left hand be? And the answer was your left hand should be in your back pocket, because if you get a large shock between your right hand and your left hand, the electric current from that thing has to go through your heart on the way from one hand to the other. But if your left hand is in your back pocket and you get a bad shock, the path of the current goes from your right hand through your feet. Still not a good thing, but it doesn't go through your heart. It can go from your right hand to your feet without going through your heart. And so that's considered safer, although still not something that you want to have happen. You want to be a little more careful with that. But anyway, accelerating about 25,000 volts. So find the magnitude of the electric field in that region if the separation between the plates is only 1.5 centimeters. Oh, well, delta V, that's the 25,000 volts. Okay, that's going to equal the electric field times the distance. And so you can imagine that you've got some positively charged, actually you'd have a negatively charged plate backmost, and then you'd have a positively charged plate toward the front, probably with a little hole drilled in it for the electrons to zip through after they've been accelerated. The electrons would be repelled by the negative plate and attracted toward the positive plate, and the ones that happen to go through that hole are then moving at a nice brisk clip. And actually you'd probably have the charges on the inside of these plates, not on the outsides. That way the electrons that go zipping through that hole, then this back side of the plate might actually be neutral. And so if they got through that hole, they just kind of keep going, and they go up and hit the front of the tube. And the old picture tubes had phosphorescent paint on the inside of it, and they'd glow. When we were kids, where we lived in Spokane was right on the edge of town, and people used to go and dump garbage instead of paying the $1 fee or whatever it was at the dump in those days. They'd just dump garbage out not too far, just a couple blocks from where we lived. And we'd go over there, and one of our favorite finds is if somebody left a TV set there, because this whole thing in here was a vacuum tube. And if you threw rocks at it, once you broke it, it would implode. And that was always kind of impressive for us kids to see, was this imploding TV tube. We'd stand back a ways when we threw the rocks at them. But big fun. In those days, it was hard to keep yourself entertained, so you had to do stuff like that. All right, so anyway, E times D is going to equal those 25,000 volts. Well, there's the D, 1.5 centimeters. So the electric field in that case is going to be 25,000 volts divided by 1.5 times 10 to the minus 2 meters. And I've run overtime today, as usual. I need a clock on the wall to remind me. Okay, and I get about 1.7 times 10 to the 6th volts per meter, which is getting up there. I think it's, it might be either 3 times 10 to the 6th volts per meter that, it might be that much. I can't remember for sure. But it's around that. That's the breakdown strength of air. But there's no air in these things. It's in a vacuum tube. So there's that. Okay, we'll stop there for today. And tomorrow move on with some more stuff having to do with electric potential. So read the first few sections of chapter 21, 22, 23 carefully to start getting a bit of a conceptual understanding and familiarity with some of the terms having to do with electric potential energy and electric potential. So stop my share there, and let's see, I need to, I have to run out to school today, but not for your class. It's for the Physics 114 class to do a lab for them. But I'll stop here and be watching. I'll get the sample problems posted and other things as well. So later.